Hello everyone, the topic of our discussion today is the pre-laboratory introduction to experiment titled Colorimetric Determination of Aspirin in Commercial Preparations. The reason why we are doing this experiment and I decided we will do this in person is because it shows a variety of important analytical chemistry techniques such as preparation and dilution of solutions, as well as we're also going to talk about Beer's law. If you recall, we discussed Beer's law briefly in Chem 1240, and now it's time to sort of delve into a little bit more depth as far as Beer's law and define some additional parameters within it, and also discuss how it's going to be used in experimental chemistry. Because Beer's law is so important and such a widely used relationship in general and analytical chemistry, and you're likely to encounter it again in both chemistry and biology. So we're once again looking at aspirin, and at this time the general goal of this experiment is to quantitatively determine aspirin content in various commercial preparations. These days in the supermarket or pharmacy, we can find a variety of medicines available over the counter that contain a mixture of several pain-relieving ingredients, and aspirin is often one of them. For example, aspirin is often combined with caffeine and acetaminophen in a medicine similar to Excedrin. You probably have heard of Excedrin, very widely used headache medicine. It is believed that this combination of aspirin, caffeine, and acetaminophen would help fight headaches better than single ingredient medicine. And so goal here is to find mass percent of specifically aspirin or acetyl salicylic acid in such preparations. Aspirin, of course, as you may recall from our previous lab, is a white solid. When it dissolves in water, it produces clear colorless solution, which would make it impossible to measure the absorbance of. We discussed it briefly in Chem 1240. I told you that when measuring absorbance in visible range of electromagnetic spectrum, one required parameter which you can sort of assess quickly using your eyes as an instrument is the color. The substance or solution will only absorb color or absorb light, in visible range, assuming it is colored. If a substance is colorless or solution, then it means that absorbs equally or doesn't absorb equally along entire wavelength range. So here we're dealing with acetyl salicylic acid. Here is its structure. It should be familiar to you from before. We discussed the fact that it has a benzene ring, carboxylic acid, and an ester group. And because it's colorless, before we can measure its concentration based on its absorbance, we need to transform it chemically. To do this, after measuring 0.4 grams of clothes into your flask, you're going to add sodium hydroxide solution, and you're going to very carefully heat using a hot plate. Now, heating a solution that's basic, obviously sodium hydroxide is a strong base, has to be done very carefully because basic solutions tend to sputter when heated, and so you're going to have to do it really carefully and controlling the heat. Heating should be done for a prescribed amount of time. The exact time is in your procedure. And then once the solution has been heated, it will basically, sodium hydroxide will basically break up the ester group, and it will also break the acidic hydrogen off of carboxylic acid group, creating this diion. So you have a negative charge on this oxygen because your entire group here broke off, and also your hydrogen broke off. After you heat, you're going to transfer the solution into large 1 liter volumetric flask, and you're going to add several, first you're going to add water and simply dilute it to create 1 liter of your stock solution. And then once that's done, you're going to prepare a series of standards, but you need to introduce a color-forming reagent in order to allow the solution to gain color so that it would absorb light and provide you with meaningful absorbance readings. So After taking a portion of stock, you're going to add a special yellow solution that will be available in large yellow containers in the hood. And that solution actually contains 3 ingredients. First one is hydrochloric acid, which of course, being a strong acid, generates a lot of hydrogen ions. So by adding H plus to your dye ion here that's present in your stock, you're going to put hydrogen here to reform or recreate a carboxylic acid group, and you're also going to put the hydrogen right here on this oxygen, which of course generates another group that should be familiar to you. It's our OH group attached to a carbon, which is a part of the benzene ring, which of course we know, hopefully you know now, is called the phenol group. And the structure of this product here should be familiar because this is salicylic acid, which we used in our previous experiment to make aspirin. So basically here we're going in exactly opposite direction to the reaction we performed to make aspirin. There we started with salicylic acid and we made aspirin. Now we're transforming aspirin, or ASA. ASA is abbreviation that stands for acetylsalicylic acid. So we're taking acetylsalicylic acid, treating it with sodium hydroxide, followed by strong acid, and that allows us to recreate salicylic acid, which of course contains phenol group. Why do we need that phenol group? Well, you may recall that we also looked at the reaction that we use for qualitative testing or qualitative testing of aspirin, where we use a substance called ferric chloride to tell whether phenol group was present or not. And we mentioned that when phenol group is present and it's combined with ferric chloride, purple complex results. And so here we're taking advantage of this very reaction in order to convert our salicylic acid, which used to be aspirin, into purple material. I'd like to point out that all reactants here, including NaOH, H plus, and FeCl3, are all added in excess so that the amount of purple complex will be proportional to the amount of ASA we started with, because ASA basically acts as a limiting reactant. So I started talking about that yellow solution that will be in jugs that you'll be adding to a certain amount of your stock solution. So what are the ingredients in that yellow solution? Well, HCl is a source of H+. Second, of course, is FeCl3. If you recall, FeCl3 is yellow in solution, so no surprise there. The solution in those big brown containers in the hood will be yellow. And the third third component is potassium chloride. Potassium chloride is used here to maintain same concentration of ions overall in solution, so that absorbance is not affected by varied concentration of overall ions in solution. So potassium chloride is basically an inert ingredient there added to maintain same ionic strength of the solution. So how are you going to do this? Well, once purple complex is formed, you're going to use that to your advantage, and we can measure absorbance using a spectrometer. And the spectrometer will first ask you to find what's called analytical wavelength. And this is the first definition that you need to be familiar with from this experiment. So analytical wavelength is defined in your lab manual as the wavelength where percent transmittance is the lowest. Now, percent transmittance is a parameter that's sort of opposite to absorbance. If absorbance shows how much light is retained by the sample, percent transmittance shows how much light has gone through compared to how much light has come in into the sample. Since we're exclusively using absorbance measurements using our new spectrometers, we can define analytical wavelength as the wavelength where absorbance is the highest or is its maximum. However, I will also accept the definition given in the lab manual, which says that analytical wavelength is the wavelength where percent transmittance is the lowest. So either percent transmittance is the lowest, or absorbance is the highest, or is its maximum. And because the solution is purple, you will see when you run the spectrum that the peak happens to be at right around 530 nanometers. Typical absorbance spectrum is diagrammed on figure 3 in your lab manual on page 52. As you can see, what it shows is absorbance on y-axis and wavelength on x-axis. So absorbance is on y, wavelength is on x. This range here from about 300 to about 800 nanometers is a typical wavelength range for visible portion of the spectrum, meaning our eye is sensitive to this type of wavelengths in this range. And as you can see, when you're measuring absorbance of a solution, it's not the same across the entire range of wavelengths. You typically have a well shown or well expressed maximum. So looking at this curve, how would you find analytical wavelength? Well, you would look at the portion of the curve where absorbance is the highest, right here, and you would then go down to x-axis, and it shows right around 530, maybe 540 nanometers. And that's how you would know how to find analytical wavelength. So in the quiz, if I gave you a graph similar to this, and I asked you to find analytical wavelength, and you have absorbance up here on y-axis, you would simply find a portion of the curve where absorbance happens to be the highest, and carefully go down to x-axis and find the wavelength at which this maximum of absorbance occurs. So once you know at which wavelength you should be measuring all your absorbances, you can then take all your standards, which will all be purple, of course, but they will be varying degree of purple because the concentration will be different of your purple complex, because you will be using a varying amount of stuff to make that standard. We'll discuss that in a separate video. But here is that very important analytical relationship that everyone taking chemistry courses must be familiar with. It's called Beer's law. It basically shows the relationship between molar concentration of light absorbing species and the absorbance of light. So A here stands for absorbance. This absorbance is typically measured at analytical wavelength. This here is the Greek letter epsilon. We'll discuss its meaning in a second. This here, B, represents the distance light has to travel through the sample. In scientific terms, it's often referred to as path length of light through the sample. Finally, C here stands for molar concentration of light absorbing species. So let's talk about this epsilon right here. The Greek letter epsilon is used to designate a parameter called molar absorptivity, or sometimes when reading scientific literature, you may also see that it's referred to as extinction coefficient. And we'll discuss its meaning in a minute. Again, B is path length of light through the sample or through the solution. In other words, it's the distance light has to travel through the sample. In old spectrometers, we use special test tubes. So B was equal to the diameter of the test tube. Now, because we're using rectangular cuvettes, it's basically the width of the cuvette, which happens to be equal in all of these cuvettes, which are carefully calibrated for their width. This B, this distance light that travels through the sample, is equal to exactly 1 centimeter. In most applications, regardless of the model of the spectrometer, typically B is equal to 1 centimeter. And so we treat Beer's law in terms of graphical representation. So you're going to have to create what's called a calibration graph. You have done this type of calibration graph for Beer's law before in Chem 1240, so hopefully this is more or less a review for you. So what I did here is I wrote Beer's law, and then right underneath it I wrote equation from algebra that represents a linear function, in order to show you that absorbance is directly proportional to molar concentration. So if we plotted our molar concentration on x-axis and we plotted our absorbance on y-axis, we would be expected to get a linear graph. And there are two important features that we need to discuss here. First of all, the product of epsilon and b would give us k, and k in math is referred to as slope. And the fact that because b is typically 1, then molar absorptivity, or epsilon, would be expected to equal to k, or slope of the graph. So the meaning of molar absorptivity, expressed by using this epsilon here, is slope of the graph, which of course shows how steep the relationship is and how much of a change in concentration causes in absorbance. We will discuss this a little further next, but first I would like to also point out that in this graph here, in this, not graph, but in this relationship, typically in math, the equation for linear relationship would be y equals kx plus b, and b would be called y-intercept. As you can see here in Beer's law, there's nothing. Here, there's no y-intercept. What does that mean? Well, it means that y-intercept in this particular circumstances equals 0, and that means that the equation would be expected to start at the origin. So in this next diagram, I'm showing two potential, or hypothetical, I should say, Beer's law graphs. So I have absorbance on y, I have molar concentration in moles per liter on x, and I have two graphs. Both are linear, both begin at the origin or have y-intercept equals 0, but obviously there are two different graphs. So what is the difference between the two? Well, the difference is clearly the slope. So which slope do you think is greater, for graph 1 or graph 2? Considering graph 1 is obviously steeper compared to graph 2. So hopefully you can see that graph 1 would be expected to have greater slope compared to graph 2. What does it mean for our discussion? Well, what it means, I went ahead and I showed you how slope is found. So for lab quiz, you are expected to be able to find slope and know that slope is equal to molar absorptivity here. So if I asked you to find molar absorptivity, you would basically be finding slope. But how do you find slope? Well, you do rise over run. And I'm showing you how I did it for these two hypothetical graphs. I take rise over run for both. And as you can see, for the same run, so this is my run obviously on x-axis, and I have close to 0.006 for my run for both of them. But rise is significantly different for both of them. So if I have this run here, my rise for graph 2 would be about 0.2. But for graph 1, my rise would be over 0.35, so it would be closer to 0.4 possibly. So obviously, much greater response in y parameter, which is our absorbance, to certain change in concentration, meaning graph 1 has greater slope or greater molar absorptivity. I would point out that for solutions that are intensely colored, like in our case, the solutions will turn very dark purple once ferric chloride is added to the stock. Such solutions typically exhibit very high molar absorptivities. In my example, the molar absorptivities that I found were about 40 roughly for graph 2 and about 100 for graph 1. However, it's not atypical for molar absorptivity to be in hundreds or even thousands for some solutions. And typically your eye can even tell you whether you can expect high molar absorptivity or low molar absorptivity. Basically, if you have small concentration of solution and yet very bright intense color, it might mean that your molar absorptivity is going to be high. If on the other hand you have fairly high concentration of solution and it's colored but not intensely colored, and colors sort of faint maybe would be term to use, then it means that molecular activity would be expected to be fairly low, which is what I summarized for you right here.